Rita Jiménez Rolland. His talk is Representation Stability in FI-módulos.
Well, thank you for all of you for being here and for Kike for the invitation. I was joking that this is the talk that is going to be about temas afines, more than categories and a bit of algebras maybe, but I guess what I intend to do is like a survey talk in these two topics that somehow are related with some notions that may be of interest for the audience here. So let me. So more than representation stability, I'm going to find this notion of multiplicity stability. And my definition is not going to be as precise as I should be. It's going to be more like, I'm going to illustrate with examples what I mean by that. And part of the motivation of this is sort of like some patterns that Church and Farb observed back in 2010. They were studying cohomology of some families of groups and spaces. And they observed some patterns, so they formalized the notion that they observed, and then this gave rise to a whole theory that this is the thing that I'm going to speak about. So just a couple of references about this. Most of the sort of like introduction that I'm going to give to this topic is following this brief introduction to representation stability by Jennifer Wilson. There's a version of this in her webpage where you can follow most of the ideas that I'm going to be talking about. And something that is very good about her sort of her introduction is that she has plenty of reference of the subject. So if you are interested in this topic, that's a good place to start. And then this notion of representation stability or multiplicity stability I'm going to talk about was introduced first in this paper by Church and Farb, Representation Theory and Homological Stability. So let me tell you what I mean by that. So my notation for this talk is going to be S sub n is the symmetric group on n letters. And I'm going to be considering at the beginning rational SN representations, usually of finite dimension. And we know that they decompose as direct sums of irreducible representations, and also that there is a canonical bijection between irreducible representations and partitions of n. And just to establish my notation here, B sub lambda is going to denote the irreducible representation that corresponds to the Young diagram lambda. And in case you are not familiar, just to put the ideas in context, here's the example. So that's going to be the notation for the S4 representation that corresponds to the partition 3, 1, and this is the Young diagram representation of these partitions, 3 boxes in the first row and 1 box in the second row. So I'm going to be playing with this sort of bijection that exists between partitions and irreducibles. And so let me try to illustrate this notion with a simple example. So I'm going to consider the following sequence of representations. This is Bn. Bn is going to be a vector space of dimension n, and I'm denoting by E1, E2, up to En, all the basis of this vector space. And I'm giving an action to this vector space, which is the following. I'm just permuting the basis elements by acting on the indices of the basis elements. And something to notice in this example that we can see like very easily is that if you look at the decomposition into irreducibles, into Sn invariant subspaces, you get always a direct sum. The first one, if you notice, is a one-dimensional vector space, which is generated by this sum, E1 plus E2 up to plus En. And the second one is the orthogonal complement of this. So I just put this figure to illustrate what's going on. This is the first case when n equals 1, it's just a one-dimensional vector space. The case n equals 2 is going to be one of the subspaces is this one, and the other one is the orthogonal complement. And then here we notice that one is of dimension 1, this is the first component, and the other one is going to be of dimension n minus 1, in this case 2. And so what I want to point out, and this is the notion that I'm illustrating here, is that if I'm using the notation that I was establishing at the beginning, well, notice that for B1, I get a trivial representation. It corresponds to the Young diagram that I'm putting there. For B2, which is this example, I get a trivial rep and a trivial rep. For B3, I get a trivial rep plus this representation of dimension 2, which is called the standard representation, which is the one here. It corresponds to this plane. And then if I continue to see what's going on, or I use this notation for the decomposition that I have there, I always see something like this. So which partition is this? Well, remember, so I'm saying Qn. I'm using the notation to say that Qn is a trivial rep, Sn rep. And this is the one that corresponds to the Young diagram that has n here, which is the partition n given by n. And then I'm saying there's another piece, which is this standard rep, which, if I use the corresponding Young diagram, is the one that has n minus 1 boxes here and 1 here, which is the partition n minus 1, 1. And I'm calling this multiplicity stable because in this decomposition, no other ones appear, and the multiplicity of appearance for these two stabilizes. Look at this. Here, the trivial one appears just once. Here it appears twice. But then after this, you just get a copy of the trivial one and a copy of the standard one. And one can sort of like understand this pattern as looking at the Young diagrams, and what's happening is this. Once n is greater or equal than 3, this pattern continues. One can obtain one row of the decomposition from the previous one by adding a box to the top row. So notice, and I'm just going to write it here. So if I have B3, what I'm looking at is that here I have, sorry, I'm just not copying what I had there. So I have this trivial one, and then the standard one. And then if I want to obtain B4, the pattern that I'm following is I am adding a box here, and maybe I can use the fact that I have colors. I'm adding a box here, and then I'm adding a box here. And notice that I can obtain B5 by doing the same. I'm just going to add another box here, another box here. And there's like the multiplicity of this type of representation is 1, the multiplicity of this type of representation is 1, and the multiplicity of all the other ones is 0. And that's why the notion is called multiplicity stability. Please stop me if I'm going too fast or something is not clear. And well, as often happens in mathematics, this is not a new phenomenon. This was observed before. In particular, Murnaghan studied tensor products of irreducible representations. And for instance, I put an example there. So I'm taking, just forget about the dots for a minute. If I take representations of S8, I'm tensoring 2 of them, and then I'm writing the decomposition into irreducibles. What he observed, or what he could prove, was that if I want to know what is the decomposition once n is bigger or equal than 8, what I can do is just, again, the same rule. I can just add a box to the top row of each of the previous irreducible representations that appear in my decomposition. And one can write his term as follows. I'm taking the tensor product of these two. Here the lambda is sort of the information that goes below the top row of the Young diagram, and the mu as well. And then once I have an n, I can just sort of complete the top row so that I get a Young diagram for n and a Young diagram for n. So he proved that this tensor product can be written as a direct sum of representations. Those are irreducibles. And these are the multiplicity of these irreducibles, and what he proved is that these Kronecker coefficients are eventually constant. In this new language, this is saying that this sequence of tensors satisfies multiplicity stability. And another example, just for motivation, and this is more like the setting that I'm coming from and why I care about this type of phenomena, and it's the cohomology of the purebred group. So I'm going to denote by Bn, the algebraic group on n strands. This is the same as the fundamental group of the configuration space of unordered points in R2. And Pn is the pure braid group on n strands, which is those braids that don't permute the points. That is to say, this is the fundamental group of the ordered configuration space, ordered configurations in R2. Those two are related by a short exact sequence. So I can see how each braid permutes the points, and the kernel of these homomorphisms is the pure braid group. And this short exact sequence gives me a conjugation of Bn on Pn by an action of Bn on Pn by conjugation, and the induced action in cohomology factors to the action of the symmetric group. So that is to say, here I have a sequence of vector spaces that come equipped with an action of Sn. And moreover, I can connect this one with the case of n+1 points by looking at what are the induced maps of the forgetting, the map that forgets strands. So just since I am not putting more details here, I'm just going to point out. So Pn, let's just for an example, P4, I'm taking the elements here that are braids on 4 strands. The fact that they are pure means that they need to come back to the same point. So that's not allowed. And then to this one. And then I'm saying I can relate this to P3. And the rule can be forget the 4th strand. And here I have a well-defined notion of the 1st, the 2nd, the 3rd, and the 4th strand. So this is going to give me a braid, a pure braid in 3 strands, which is just precisely the one that forgets. The 4th strand. And what I'm looking at here is what it gives me induced in cohomology. So if I take HQ cohomology of these groups, well, this is contravariant, so it's going to go in the opposite direction, and this is what I'm putting here. And what I'm saying is that each of these comes equipped with an action, and they are related by these maps that are S3 equivariant in this case. And so this is sort of the sequence that Church and Farb were looking at, and just they computed the same. And look at what happens, and I think I fixed the mistake. So look, I think that here sort of this multiplicity stability is well illustrated. When I have 2 strands, I just have a trivial rep. When I have 3 of them, new pieces appear, so I have a trivial rep and a standard one. But once n is bigger or equal than 4, I have 3 reducibles appearing, each with multiplicity 1 and nothing else. And again, I can obtain this row from this one by the same rule. I can add a box in the top row, and then I recover the decomposition as before. And so, well, this is, I mean, I'm giving you in all these examples the explicit decomposition, and one can see that the pattern is there. But in general, this decomposition is not known, just for small values of Q, like H1 and H2, for instance. And what they proved after observing this is that this is true for every Q. So that this sequence, if you're computing the Q'd cohomology of Pn with rational coefficients, all of these come equipped with the corresponding Sn action. And if you look at the decomposition, what you can say, you don't know what the decomposition is explicitly, but you can say that this type of pattern is going to appear. These are going to be multiplicity stable once n is bigger or equal than 4q. And something else to mention about this is that this first proof was combinatorial. It was more like about understanding this sequence and how it decomposes into a sum of induced representations. So, and I guess my sort of like interest in this topic comes from the fact that I'm interested in this type of sequences of groups that appear in topology. So another consequence of this, a consequence of this phenomena can be said in this particular case for another sequence of group. So what we concluded here is that we have this multiplicity stability for the pure braid groups, but I gave you another sequence of groups, which was the braid groups. And it turns out that the dimension of those vector spaces is related to the dimension of the invariance of the cohomology of the pure braid group. So this is actually telling me this dimension is the multiplicity of the trivial representation. And if we look at the decomposition before, how many times the trivial representation appears? Well, in this particular example, we see that it appears just once. And this multiplicity stability tells us that whatever the number it is going to be constant once n is bigger or equal than 4q, sorry. So what can we say for multiplicity stability of Pn? We get that these dimensions are going to be constant once n is big enough. And this is another phenomena that appears in topology, which is we say that a sequence of groups or spaces satisfies, and I'm going to call it cohomological stability because I'm dealing with cohomology, if the dimension of those vector spaces are constant once n is large enough, which is the case here. So what I'm concluding is that multiplicity stability of the cohomology of the pure braid group is giving me homological stability over Q for the cohomology groups of Bn. And well, this is sort of like the baby example, but actually one can say more. So, well, the first result is the one that I mentioned that says that there is a multiplicity stability pattern for the pure braid groups, and in particular, it implies rational homological stability for the braid groups. This is another result of, I think that this is AD or something like that. I have a typo there. More recently, and after this sort of language was developed, Church proved that the cohomology of order configuration spaces of oriented connected manifolds of dimension d greater or equal than 2, that has also multiplicity stability. And one of the consequences of that is that you get homological stability for unordered configuration spaces. And I should point out, this result was well known for open manifolds, even with z coefficients. But this approach and the proof that by Church was the first proof of this fact for closed manifolds. So this was giving you like a different way to prove this type of results, and he could obtain a new result in this direction. And well, all of this is in this paper that I'm quoting here. And finally, more related to my work, I've studied these patterns for the pure mapping class group of orientable surfaces. And as a consequence, one can recover homological stability for, and here, delete the pure because this is not true, for mapping class groups of orientable surfaces, which is well-known results of Harrer. So let me try to sort of like relate this maybe more for the topic of this conference. So I guess one of the questions, so I guess the type of question that I'm interested in is like which other sequences of natural groups that appear in mathematics have this kind of pattern, but maybe a more conceptual question is what is the underlying structure that is driving these multiplicity stability patterns? And the answer was given by Church, Farber, and Ellenberg, and is the following, is that this sequence of representations that we are considering are what they call finitely generated FI-módulos. So let me give you what is the meaning of this notion. So I'm going to call the category FI. It's going to be, this is the language that I use. This is the category that has objects, finite sets, and morphisms are injective maps. And you know better than I know that this category has several names. I mean, it appears everywhere. And I'm going to be referring to the skeleton of the category instead of the category FI. So I'm going to be considering the category that for each integer, I have one object, which is this. And the morphisms are the inclusions of this type of set in the following. So the endomorphisms are these ones. The morphisms are generated by this, and the morphisms of an object plus the standard inclusion. So this is just a picture of the category there, a simplification of it. And what I'm going to call an affine module of a commutative ring, in my context is Q. This is going to be a functor from this category to R modules. So the data of an affine module is precisely a sequence of representations with equivariant maps. So this is the type of study that I was describing here, before, with all the examples that I put there. So I have representations, so it's vector spaces, in this case with actions of the corresponding symmetric groups, and then I have maps that relate them. So the category that I'm going to be studying is the category of affine modules over R. The objects are affine modules, the morphisms are natural transformations between them, and there are well-defined notions of submodules, quotients, kernels, cokernels, direct sums, tensor products. This is an abelian category. Some examples, just to keep in mind what I'm talking about. So those are sequences of representations that have the structure of an affine module. So one of them is the sequence of trivial representations, and the maps between them are isomorphisms. So this is like a baby example. The other one is the one that I talked at the beginning. I'm taking the canonical permutation representations with all the corresponding inclusions. I can take wedge powers of this, or I can take this sort of like polynomial algebra with the diagonal action on monomials, and then take also the obvious inclusions. And finally, this is my other example, which is the cohomology of the pure Bray group, the one that I talked about before. A non-example, not all sequences of representations are affine modules. A non-example is when I'm taking, instead of trivial reps, I'm taking alternating representations. So then it's not going to be functorial. And well, another ingredient was this notion of finite generation. So what does it mean to be a finitely generated module? Well, it's going to be the notion of finite generation that you can think of. So I'm going to say that an affine module is generated by a set if B is the smallest affine submodule containing S. And it's going to be generated in degree less or equal than B if it is generated by a set that lives in between degree 0 and degree D, in the first D pieces of the affine modules, of the pieces of the sequence. If D is finite, I'm going to say that it's finitely generated, or it's generated in finite degree. If the set is finite, I'm going to say that it's finitely generated. And something that one can check easily is that finite generation is preserved when taking finite sums, tensor products, and extensions. Something that is not as immediate, but can be proved, is that if R is a commutative Noetherian ring, then any submodel of a finitely generated affine module over R is itself finitely generated. And this is going to be a key property to sort of like use this type of approach to give answers about multiplicity stability in particular. So let's go back to pure Bray groups again. So I mentioned before the sequence that I was considering of cohomology groups assembled to form an affine module over Q. And it's a classical result of Arnold that this cohomology algebra looks like this. So it's generated as a quotient of the exterior algebra on the symbols that are live in degree 1 that I'm denoting alpha sub ij. And then if one look at one particular k, well, those vector spaces, this term of Arnold is telling us, are spanned by monomials of the form those wedges here. And notice, I mean, I can have that I, j, and then j repeats in this, and then k. Or I can have I and j, and then completely different k and l. Those are the types of monomials that appear. So if I look at this as an affine module, and I look at my definition of finitely generated, what I can notice is that this is finitely generated, and I just need this generator and all the affine action to get all the affine module generated. So because the symmetric group is going to give me the different indexes that I need, and I also have these inclusions that allow me to add n's as much as I want. And in general, it's just a consequence of this term of Arnold. that this is a finitely generated FI module in degree less or equal than 2q. And well, back to the question that I asked at the beginning. So what is the structure that derives multiplicity, or that drives multiplicity stability? So the answer is the following. If V is a finitely generated FI module over Q, then the sequence of rational representation is multiplicity stable, following the definition that I gave you at the beginning. And sort of the key ingredients of the proof are noticing that every finitely generated FI module is a quotient of a finite sum of representable FI modules. So I'm thinking of modules of this form. And one can check that each of these one is multiplicity stable. It's more like a combinatorial proof. And the other key ingredient that one needs to prove a term of this type is the Noetherian property that submodules are also finitely generated. So I guess this is sort of like an answer of what is the structure that is giving us multiplicity stability. Well, I need to encode all the sequence as an FI module, as one object, and then noticing that this object is finitely generated in this sense is going to give me multiplicity stability. Another consequence of finite generation is that I have finite presentation in type FP infinity. That is to say that if V is a finitely generated FI module, then it admits a resolution by finitely generated sums of representable functors. More consequences of finite generation, actually. Here I'm recording again two of them, the ones that I just told you before. So if I have an FI module over Q that is finitely generated in degree less or equal than D, then I have multiplicity stability, which is what I mentioned before. I have finite presentability, that is to say that it is finitely presented as an FI module. But I also have control on the growth of the dimensions. So these dimensions here grow polynomially on n. And the characters of the representations are polynomials that are polynomials that somehow, maybe I didn't say it here very precisely, but I can be more explicit. So this polynomiality of the character says that for n large enough, there exists a polynomial that lives so that the character of the representation is given by the value of this polynomial in H sigma, where each of these variables are the class function that count the number for R cycles in sigma. So, well, this polynomial has a fixed degree, and the degree doesn't depend on n once n is big enough. And all of them can be recovered by just considering the character polynomials of this form.
What do you mean by cycle?
This is an element of ns and Sn. And then you can write this in a cycle decomposition because you are elements of Sn. It's a product of cycles. And you can count how many R cycles are in this decomposition. And notice that this definition doesn't really depend on n. I can always count R cycles independently of n. So, yeah, for instance, if I have something like, maybe this is not a cycle decomposition, but here if I want to count how many tricycles I have two of them, and I have 1 2 cycle. So these are counting how many of those cycles there are, and this is a polynomial on those cycle counting functions. And what this is saying is that this character is given by a polynomial of this type. So it gives you like strong restrictions about the type of characters that can appear in the sequence that we were considering. And all of this just follows from finite generation. So, and I guess what I wanted to point out here is just that this language, more categorical perspective, is giving you a way to reinterpret the sequences of SN representations as functors from A5 to vector spaces. Then this notion of multiplicity stability that I talked about at the beginning is translated in a notion of finite generation or Noetherian property. The Mornagan stability that I referred at the beginning is just saying that if I have two A5 modules that are finitely generated, then the tensor product is also finitely generated. And moreover, the fact that I have something that is presented in finite degrees can be translated in a precise way into an inductive description of the sequence in terms of terms that appear up to a finite n. And I guess sort of this reframing gives, for a lot of examples, a conceptual explanation of what's going on and an easy to check criterion for multiplicity stability. For instance, one can prove easily from Arnold's results that the cohomology of pure-Baire groups is multiplicity stable without doing all the combinatorial magic that they did. You just need to use Arnold's results, and finite generation gives you multiplicity stability. And also, once you make this definition, you can make sense of what is a finitely generated A5 module over the integers or other coefficients. So it doesn't need to stay on Q coefficients. You can change the coefficients. And it makes sense of, you can make sense of finite generation even if you cannot make sense of multiplicity stability. Multiplicity stability is very restrictive to the rational representations. But if you are not about the rationals, it doesn't make sense. But you can still make sense of being finitely generated as an A5 module. And also this framework can use tools from commutative and homological algebra to study sequences of representations. A lot of sort of the ideas that have been developed in the recent years come more from analogies from commutative and homological algebra. So I guess I don't know how I'm doing in time. Here are other categories that have been studied with this perspective that encode representations, sequences of representations of interest. So a representation of a category, I'm calling this a function from a category to vector spaces. So those are some examples of the category that recently have been studied. So the one that I described at the beginning is A5, which are finite sets and injections, and which was used to study cohomology of configuration spaces. But then there are all these variations that you can see there, and you can sort of ask, what are the finitely generated blah modules? And they have been successful to give some sort of information about this example, in particular, homology of spaces of interest, unipotent groups, or the compactification of the moduli space. And so maybe for this audience and for people who are more interested in sort of all the categories that can play a role here, I would recommend to go to these references. Stephen Sam and Andres Noder are more interested in sort of the representation theory and category theory behind the stability patterns. And I guess George Farb and maybe the students there, we are more interested in the topological applications. But there's a whole study in that direction. And just to finish and to relate this with my work a bit, so I applied these sort of techniques to get a result about the cohomology of the pure mapping class group. So I'm just going to recall briefly what I mean by that. I'm taking S as surface, and the surface can be orientable or non-orientable. I'm putting some restrictions on the type of surfaces. Those are compact surfaces, and I'm putting a bit of restrictions of which ones, but I think most of them are there. And then I'm considering a finite set of points in the interior that I'm going to call the punctures. So just to have a picture in mind of which groups I'm studying. So if I'm taking an orientable surface, say with no boundary, but it can be in half boundary, it doesn't matter. I'm fixing some points in the interior. And the group that I'm interested in is, I'm taking diffeos from this surface to itself, I'm asking each of these diffeos to fix the punctures, and the group that I'm considering is called P mod n of sigma, and it's going to be, I'm taking pi naught of the group of diffeos that fix the punctures. And if the surface is orientable, I'm taking this orientation preserving. If not, I'm taking all the diffeos. So just to have a couple of examples in mind, if you take the disk, so sigma 0, 1, this is just genus 0 with one boundary component, and I put endpoints here, turns out that P mod n of this is just the pure braid group that I mentioned before. If you take the torus with one mark point, what you get is SL2Z. And so this is sort of a way to generalize the notion of pure braid group. It's like another sequence of groups that are related to this one. And one can prove that the cohomology of these groups, and here it doesn't need to be rational, you can pick any abelian group, those sequences assemble a finitely generated FI module. So in particular, if you want to have a result like that, we have the consequences. And the consequences is that we have representation stability or multiplicity stability, as I said before. Once I put rational coefficients, so these are multiplicity stable, even if I don't know the decomposition, I can conclude that. I have these polynomial characters that I mentioned before. Another consequence is that I have a stable inner product with character polynomials. And moreover, there's like a version of homological stability that can be recovered for the corresponding groups. This played a role as the braid group was playing before. These are the non-pure mapping class group of the surface. And I guess this is what I wanted to tell you. Thank you for your attention.
Any questions?
Yeah.
Well, I have maybe you can tell me this is an example of a model.
Okay.
I have a question. Suppose you have a matrix group, well, that is that it lives in a matrix group. No? So this has a canonical representation, and you can tensor all you want. So you take the n tensor, and this gives you the functor in order to construct an FI-module. And this theorem of I don't know the name, Magaraba or
Murganov, I don't know how you pronounce it. The tensor one.
They say that in some moment it's going to still.
The decomposition, the multiplicity, so the canonical coefficients are going to be constant.
So you are taking the same representation. You are tensor with itself. Yeah.
I guess this is, but yeah, a consequence of this. So this is saying that if you are tensoring this is sort of a sequence of irreducible representation that have the same lambda below the top row. And so the sequence n gets bigger. What is getting bigger is just the top row, and you are tensoring this with another one of this type. So you're fixing whatever is below, and then as n increases, you are just adding boxes to the top row. And so this result says that if you tensor those, and you look at the decomposition, you can always look at the decomposition with the same rule. So you forget about the first row, and then you just complete so that you get a representation of Sn. And this says that the multiplicity, the times that this one is going to appear, which are these coefficients, are going to be constant once n is big enough.
But it doesn't work if you take another representation, not that is in.
Well, one of the consequences is you can prove that whatever you put here is finitely generated in the sense that I mentioned. And whatever I put is finitely generated, then the tensor is going to be finitely generated. And then as a consequence, if you are working over Q, you're going to be multiplicity stable. But again, I guess I didn't understand very well your example, but I think what you need to check, one is that the things that you are tensoring are FI modules. Then you need to check that those are finitely generated. And once you have that, if you tensor, then it's just a consequence of that. I mean, it's...
No, it's going to be, because when you take the Bernoulli diagram, you have some title, stabilization. So, but you are taking the same representation, and you tensor the same representation. And
Yeah. So if the one that you started with was finitely generated, and you tensor a finite number of times, you're going to get something that is finitely generated again. Yeah.
And my question is that, do you know this Schur-Weil reciprocity?
I don't know it very well. I should, because it plays a role in this.
But in FI-módulos, is some kind of Schur-Weil representation?
I don't know the answer to that, but I know people know the answer to that. I mean, I'm not going to lie because I don't know, but I heard people talking about this. So I think it's no if there exists or there is not, or what is the problem if there is not.
Any other question? We thank the speaker.